Before actually getting into the math, I want to start with two warnings. So, about this talk. And the first warning is about kind of the cognitive load involved in the discussions we're going to have, because there's going to be 3 primes at any given time. And we have to be very careful to separate the roles of them, because sometimes they'll be equal, sometimes they'll be different, and so on. 3 completely arbitrary primes. And so I also need different letters for the 3 different primes. So I'm just going to set that up right now. So there's going to be P, there's going to be L, and then there's going to be nu. Okay? Kind of a finite place of the rational numbers, if you like. And they play 3 different roles. So what role will the P play? Well, we're going to have some base scheme that we're going to be considering, and the P will indicate if, for example, it's a scheme over Fp, so a scheme in characteristic P, then that will be that P, okay? So if we're living in characteristic P, our geometric object, then that's the P. What will the nus be doing? Well, they'll index realization functors, so. For motives. Okay, I'll explain a bit more about what I mean by that in a second, but more or less for every prime mu, there's going to be a different realization functor on motives. And then this L is where our invariance will live. So we'll live at the prime L. So for example, we could have a class in something like I don't know, H2L minus 1 with coefficients in FL. So we could have something in there that will pop out from the story. Okay, so that's the first warning about 3 primes. Second warning is about motives. So motives. And the warning is that I will not precisely say what I mean by a motive. And in fact, I'm not even thinking of a precise definition of motive. Imprecise in this talk. So I'll state a conjecture which says for every motive something happens, and then that conjecture is a priori not mathematically well defined because I haven't said what I mean by motive. I don't even know what I mean by motive, to be completely honest. However, I will say enough to, and this is the important part for me, to say how you can extract from this concrete consequences that can be verified. So I'll tell you enough about motives so that you can take this conjecture and make it into an honest conjecture by plugging in various things and so on. So you can think of it as kind of meta language for making more precise conjectures. And maybe everyone has their idea about what a motive is, and I invite you to plug it into this and make your own form of the conjecture. Okay, so with that out of the way, maybe I'll actually start with motives. So I'll start by recalling the basic idea. Maybe in the simplest context, let's say K is an algebraically closed field. Then I guess the phenomenon that motivated the theory of motives was that there are many different cohomology theories. For say smooth proper K varieties. So for example, you have de Rham cohomology. Let's say if let's just say if K is characteristic 0 for our purposes here. And you also have a closely related thing called Hodge cohomology, which is associated graded for a filtration on de Rham cohomology. And it's actually this one that's going to be more important for us, so I won't even recall what this is, but this is just, direct sum over P of H star minus P x. and then you do the p forms on x. So it's a graded vector space over the base field. But then also for every prime nu, you have a realization functor as well. So this is also for k characteristic 0. So if nu is not the same as the characteristic, then you have L-adic cohomology. So yeah. Or nu-adic, sorry. So this here is a graded vector space over K. This here is a vector space over the field of nu-adic numbers. But also if nu is equal to the characteristic of K, then you have the crystalline cohomology, which is I should put the nu in there. So that's a vector space over, well, yeah, vid vectors of K with P inverted. So then this is equal to P, I guess. Right. So you have this whole wealth of cohomology theories, and they look different. I mean, they live over different fields, for example. But there are many common features in all of these different cohomology theories. Well, they all have Poincare duality. They all have some Kuhneth formula. The dimensions are all always the same, which is not so obvious from the definitions. And there are also some comparison isomorphisms between them. I didn't write down the Betty cohomology, but over the complex numbers, there's also Betty cohomology, which has Q coefficients. And there are various comparison isomorphisms between them if your field has a certain specific nature. And this plethora of cohomology theories with various extra structures and relationships between them led, I guess, Grothendieck to posit this idea of motives. So that's very strange that it's squeaking. Okay. So idea of Grothendieck. So there should be a category, some kind of linear algebra category, complicated linear algebra category. Not vector spaces over a field, but something much more structured. Let's say motives over K, and a universal cohomology theory. So you smooth, proper varieties over K, values in motives. And then there should be so-called realization functors. So there should be Hodge realization going to graded vector spaces over K if the characteristic of K is 0. There should be nu-adic realization functors to QV vector spaces, and etc. All of these different cohomology theories you have should be explained by realization functors. And these should be additive tensor functors. So you always have additive structure and tensor structure you can play with in this category here. So it's a category of linear algebra, and it kind of is supposed to explain all the different cohomology theories or refine all of the different cohomology theories.
So may I ask a small question?
Yes.
So in the best conjecture, so of course using algebraic cycles one can construct some kind of, but this is what Grothendieck tried. But anyway, for cohomology you have HI for all I, so you should have a sequence of cohomology functors to MK. This is what you mean, that MK is a kind of...
Thank you, yes. Yeah, thank you very much. I was too imprecise here. So for all I, you have HI, which goes into there. And the I corresponds to this star that I was writing before. Yeah, thank you. And there's... and sort of...
No, but for fixed I, you don't have monoidal structure.
No, that's right. That's right. Yeah. Yes. Okay. Right. And actually related to this, well, there's some important... So for example, for all x and for all I, in natural numbers, say, we get an object HIX in this motive category. And a simple but important example is if you take H2 of P1. I should say this category is Q linear, so I'm working with Q coefficients here. Yeah, so this H2 of P1 gets no special notation. It's called Q minus 1. And an important, if you look in a usual cohomology theory at H2 of P1, it's a one-dimensional vector space, so it's invertible under tensor product. So then you posit that that should also happen in the category of motives, so this should be tensor invertible. And the dual is called, or the inverse is called, by definition Q1, it's called the Tate twist. And it's important because it's the kind of thing that shows up in Poincare duality. If you formulate Poincare duality in this context, this is kind of the appropriate dualizing object, or its tensor powers. But another much deeper but important structure on this category you have is a canonical grading. So this is called the grading by weights. So and then weights. So there's supposed to exist a decomposition of this category as a direct sum over W of so these are the objects of weight W. And it's supposed to have the property that HW of X always lies in this weight W summand. Now it's important to not get confused here. This is just say an abelian category, so it's not a derived category. So in some sense everything's living in degree 0. But nonetheless, there's supposed to be enough structure on this category of motives that given a cohomology of a smooth projective variety, you can tell which cohomological degree it came from just from sort of this plain linear algebra, so to speak, in this category of motives. So this was motivated by the Weil conjectures, where over a finite field, for example, you have an action of and you base change the algebraic closure, you get an action of Frobenius, and the eigenvalues of Frobenius will tell you the complex absolute values of the eigenvalues of Frobenius will actually tell you what weight you lived in, which cohomological degree you came in, even if you don't a priori remember the cohomological degree. So yeah, so it's an important structure, and it will play actually a big role in the talk. So oh, thank you. Yes, thank you. Yeah. Okay. Other questions about this basic motive philosophy here? Okay, so actually I'm not just going to be talking about motives over a, algebraically closed field or a field, but motives over a more arbitrary base. And I'll be even more vague about that. So more generally, can consider motives over S for S a scheme. And it should be thought of as kind of families of motives over, I don't know, residue fields bar as X varies over all points in the scheme. So a sort of a smoothly varying family of motives. And for example, so if you have a proper smooth map of schemes, then you should have an object, I guess maybe notation Ri P lower star Q. So whatever this means, it should be an object in this category, and so it's collecting together the motives attached to the geometric fibers of this smooth proper map, which are then smooth proper varieties over a field. Okay, and again, you should have a weight grading, and you have a Tate motive, which is invertible, and so on. Now, what do the realization functors look like in this case of motives over a base scheme? So let's So actually, for the moment, we consider only the case where S is actually a Q scheme. I'll say a bit more about the general case maybe towards the end of the talk, but just to keep things simple at first, let's be in characteristic 0. Then, to a motive over S, we have these various realizations. So, for example, there's the Hodge realization, and this lands in graded vector bundles on X. Again, just collecting together the Hodge cohomology of the fibers in the case where you have the motive attached to a smooth proper scheme. But then also for all mu, you get a realization with values in least Q nu sheaves on the étale site. So that's the kind of thing you get when you have a family of varieties and you look at a nu-adic cohomology. So I'll recall that a least Z nu sheaf is kind of a compatible collection of locally constant Z mod nu to the NZ sheaves on the étale site, locally constant and finite rank. And then so you have some compatible system of them. You imagine the inverse limit, that's at least Z nu sheaf. And these things are kind of like that, except, well, up to isogeny, you could say. And now I'm waiting for Gabor to ask a question.
Of course, the standard thing about non-unibranch schemes where you can have a Q nu sheaf with monodromy, which is not in the same star, like you know.
Exactly the question I was predicting, yes. Yeah, so yes, indeed. So there's two different things you could mean by this. So you could ask, maybe you only want a lattice, a Z nu structure to exist locally. This distinction is not relevant for the talk. I mean, for two reasons. One is if you start with one of these guys, you're always going to have a lattice. So that doesn't matter. But also all of the constructions that I discussed for least Q nu sheaves, they also work just fine even if you don't have a global lattice. So if it only exists étale locally, all the constructions will be étale local. So the distinction is not important for the talk. Okay. So that's kind of, so this is where we're going to be playing. We have some motive, and it has these different realization functors. And what I want to explain a strange conjectural relationship between these realization functors, these different realizations. So they are objects of completely different nature, but what I'm going to say is that somehow to each one of them you can extract the same kind of object, which I'll turn to and explain next. And then if you start with something here and you do all these realization functors, you get the same kind of object. There's going to be a relationship between them. And then after that, I want to explain the evidence for this conjecture and some practical consequences that you can extract from it, some known consequences. Okay, so what goes in the black box up there? So that's where our prime L comes in. So choose a prime L. Then this black box that I'm going to describe is going to be least sheaves not over QL or over ZL, but over the L-adic sphere spectrum. Okay, so L-adic sphere spectrum, but they're going to be of rank 1, so to speak. They're going to be invertible least sheaves over the L-adic sphere spectrum on the étale site. So there's some stable homotopy theory object that's coming in here. And note that there's some funny things about this. These are pure linear algebra, even Q linear algebra, but somehow then you extract something over this base which has a lot of torsion. So it's a little bit of a funny story where some rational story gives you a bunch of torsion information. And then there's things you can say about it. But yeah, so what is this notion of least sheaf? Well, there's different ways of giving the definition, but you can imagine writing the L-adic sphere spectrum as some kind of limit of a tower of things which only have finitely many homotopy groups, and maybe where the bottom one is z mod L to the n, and all those other homotopy groups are finite, and then it's not difficult to set up a notion of least sheaf over the sphere spectrum just in the same way as you do for least ZL sheaves, for example. But just to write down a precise definition here, let's say it's the invertible objects. So pick, in another way of saying it is you can look at like étale hypersheaves. Sorry, it's redundant. In the category of like L-complete spectra. So you look at the tensor invertible objects there. Okay, so what am I saying? I'm saying from any of these, from any of these kinds of objects here, you can get such an object here. So let me now explain that. So first case. Suppose given a vector bundle on S. Not a graded vector bundle, but just an honest vector bundle. I want to explain how to extract one of these guys. So then V, you make it geometric. You kind of make the family of vector spaces parameterized by S, which is incarnating this vector bundle. And then you also have the zero section, which I'll call E. And you can use some kind of six-functor formalism in this context. So you make the dualizing object in this world, which lives on V, and then it's going to be kind of constant because this is a vector space. So you just take the fiber at 0 to get an object over the base. And I'll call this SLV. Because what it kind of is the one-point compactification of V sort of viewed in étale étale stable homotopy theory. So it's the object that controls duality, cohomological duality in this situation here. And the definition in the new adic case will actually be pretty much the same, strangely enough. So, yeah. So second case. So let's say L in...
So in the first case, you forget about the grading.
Yeah, the grading. I'll explain. There's no grading in the first case. So it doesn't yet plug into the Hodge cohomology. I'll explain how to plug it in a second. So let's say if L is a least Q nu sheaf on S étale, then you can do something a little bit funny, which is, in some sense, you can also view this as a sort of geometric object living over S, and it's a group object, it's an abelian group object. You can take its classifying stack. It also has a projection, and it has a canonical base point. And I claim there's also a six-functor formalism for such things, and you write down the same formula. And we'll call that the L-adic sphere attached to L.
Could you just briefly recall the definition of SL?
Yeah, so SL is the L-complete sphere spectrum.
Yes, you said so.
Yeah.
And more precisely?
No. Yeah. No Eilenberg-MacLane spaces. No, so, well, yeah, so I can tell you something about it. It is a spectrum, so it has homotopy groups, and the zeroth homotopy group is the L-adic integers, and the ith homotopy group is the L part of the ith stable homotopy group of spheres.
You took the sphere spectrum.
Yeah.
And L-adic
Yes, exactly. Yeah. Okay, now I don't expect you to really understand what, I mean, this is, yeah, really understand the details of this necessarily, but just to give you an idea. Okay, so let me now, so this is, so to an object which is relatively concrete, for example, a vector bundle, I've attached an object which is relatively obscure, some kind of least sheaf over the sphere spectrum, or yeah, to one of these guys, something relatively obscure. Now let me explain what kind of concrete invariance you can extract from this situation. So what can be concretely extracted? From such SLV, or well, such objects of.
Can you maybe comment why classifying stack appears? Because on the top there is.
Just a sec. Sorry. Again?
Can you maybe comment why the classifying step appears compared to between first and second?
Yes, I can comment on that. So let's say we're working over a point or an algebraically closed field. Then you still have then you have this thing it's a finite dimensional Q nu vector space. It's a locally compact Hausdorff space in particular. You certainly have a six-functor formalism without the L, but what you don't have is Poincare duality. I mean, it's kind of clear such a thing. In contrast, if you had the real numbers, there's going to be no Poincare duality for that. So you could write down this definition, but it wouldn't be an invertible object. It would be some huge thing which is basically a distribution space on your locally profinite set, which is the underlying topological space of such an L. But when you pass to the classifying stack, it's basically a reflection of the fact proved by Lazard that you have Poincare duality for p-adic Lie groups, that when you do the analogous construction in that situation, you really get an invertible object. Okay? Maybe not okay, but I'm going to move on anyway. Yeah. So, yeah, right. So
excuse me. So if you take a list ZL sheet instead of Q nu sheet, a list Z nu sheet,
yeah.
Then you get again an invertible object, which is the same as for the associated Q nu sheet.
Exactly. Exactly.
So in fact, it's kind of local because up to etal maps, the B doesn't depend on which lattice you choose.
Completely. Completely. But the reason for doing it this way is you get extra functoriality. So yeah, you get a GLN Q nu acting on the whole situation as opposed to just GLN Z mu. So yeah.
And do you need to use here some pro-etal site, or you work with? Okay, but maybe this is a technical thing because I'm not sure how to construct these things. But
yeah, no, I mean, yeah, you should use some pro-etal site for sure. Yeah, to define objects like this. Yeah. Okay, but in the end, I mean, you can get something that lives there. Okay, right. So the first invariant is rather banal. So if you have a Lie sphere L, invertible Lie sheaf over the sphere, then you get just a continuous function from S to the integers. So yeah, at every point you get an integer, which just records the dimension of the sphere. So these, in some sense, these dualizing objects that I've written down, they live in some degree, and you extract that degree, and that's the very first, the discrete invariant you get from the situation. And what is it in each of these two cases? So maybe, I have 3 boards. Okay. So, sorry?
3 prime numbers.
Yeah, 3 prime, right? Oh, if I were more organized, I could have maybe, yeah. Okay, so for V in vect S, then what is the dimension of this one-point compactification here? It's 2 times the rank of the vector bundle. 2 times, because remember in étale theory of, well, well, you sort of think by analogy with over the complex numbers and usual topology, and a d-dimensional thing over the complex numbers is 2D-dimensional as a real thing. So the Poincare duality will be put in degree 2 times the naive dimension. So that's the reason for this 2 here. Yes. Yeah. Yeah, that was the definition of this object here. Yeah. Right. Okay. What about L in lease? Where was it? Oh yeah, up there. Lease Q nu S étal. Then what's the dimension? So it depends on whether or not nu is equal to L, right? So if nu is equal to L, it's just equal to the rank of L, this time without multiplying by 2. But if mu is different from L, then it's 0. And in fact, in this case, if you choose a Z nu lattice, you get a canonical trivialization of the whole sphere. So where am I? Yeah. Yes, in degree 0.
Sorry.
Yes.
I'm confused.
Yeah.
I mean, in the second case, you take L to be a least sheaf, but least sheaf you can have co-connective. I mean, whatever. I mean, it's not necessarily connective. How you be
connective? No. I mean, it lives in degree 0. My least sheaves. Oh. Yeah, they're totally classical objects. These least sheaves.
The first case is not classical.
No. Here and here, they're just living in degree 0. There's nothing.
No, I mean,
yeah.
The first case
here? Yeah.
Yes, because you have some spectrum.
Yeah.
It's not classical.
Well, this isn't. No, this is.
Okay. Okay, thanks.
Yeah.
Sorry, could you say what is dimension?
Oh, yeah. So, what is this dimension function up there? Yeah. So, okay. Again, if you restrict to a point of S, then you're just getting an invertible, L-adic spectrum, and that lives in some degree. We take its homology, and you get an abelian group sitting in some degree. You look at what degree it sits in. Yeah, so it's some kind of sphere, and you just ask what dimension is the sphere. Yeah.
So is that related to the dimension for a dualizable object in a symmetry model category?
Well, I mean, this and this are, but no, this is something different. Okay. Yeah. No, it's cohomological shift more than dimension. Yeah. Okay. But now I have a problem, right?
You have something there.
Here? Yeah. I'm so happy that it's old-fashioned technology, because there's been too many situations with buttons that they just don't work. I gave a whole class for 200 students where the buttons on the blackboard didn't work. It was terrible. Okay. So, yeah, okay, there's also a second invariant that you can extract. So if you have a invertible lease SL sheaf on S, then you can get a rank 1 ZL lease ZL sheaf on S. Because you can pass from this to invertible lease ZL sheaves on S étal just by base change, so by taking homology. And then this lives in some cohomological degree, which was this dimension that we defined, but then you can shift it down so it lives in degree 0, and you get one of these objects here, so shift by minus dimension. So that's the second invariant you get. And again, what is it in the various cases? So in case SV, this is just a Tate twist. So ZL, the Tate twist again being determined by the rank of V. Now without the 2. And in the case of SLL, so this is, so it's the top exterior power of some. So if you choose a lattice inside L to make it at least ZL sheaf, then it has a top exterior power, which is rank 1, and that's what goes there. So if mu is equal to L, and it's just the trivial, again, if mu is different from L. So this is after choice of lattice. Okay, so these are kind of the these are this first invariant and the second invariant you can extract from this object are kind of very normal things. I mean, they're kind of, everything can be read off from the homology. So we're not seeing anything there from the fact that they're working over the sphere spectrum as opposed to working over the integers. So these are the very basic things. It turns out my conjecture will say something interesting even on this level, but it only really starts to get interesting when you try to extract further invariants from this situation. So what else does basically a bundle of spheres have besides a dimension and an orientation character, so to speak? So there's higher invariance. So let me maybe take a break from all this fancy stuff for a second and remind you of a simple story in algebraic topology. So I guess this was Tom. So if S is now, instead of a scheme, if it's just some, say, CW complex, and then we have, I don't know, P over S, some sphere bundle, and let's give a base point too, then there are characteristic classes that you can extract from this. I'll just give the most, well, Stiefel-Whitney classes, essentially. So, which live in the mod 2 cohomology of the base. And they have the property that if P is the fiber-wise one-point compactification, one-point compactification of a vector bundle, V over S, then this Stiefel-Whitney class of P is the same thing as the usual Stiefel-Whitney classes of this real vector bundle, V. So the point of, well, so basically Tom gave a formula for the Stiefel-Whitney classes of a vector bundle, which manifestly shows that these numbers only depend on the associated sphere bundle that you get by taking one-point compactifications. So this is...
I asked about your, it's related to the previous question about the previous blackboard, where you, in the case where nu equal to L, you are working in a lattice cohomology and nu is the same. So then you want to work with QL, least QL shapes and do this construction, but it seems that this depends on the choice of a lattice. Now this wedge top.
It seems that it does, but in fact it doesn't.
In other words, if you have two lattices, then the wedge top of the lattices are isomorphic?
That's correct. Canonically. And the reason is, yeah. So the reason is simple. You take the wedge top of the QL thing, and then that, if you look in the universal case, so you have something acted on by GLN QL, then you're just getting from the top exterior power of the standard representation, you're just getting a homomorphism to QL cross. And QL cross is like L to the Z times ZL cross. And you just project off the L to the Z component. And that's another way of describing this same thing, which doesn't involve any choice of lattice.
Okay, so this is... Okay.
now it's more impressive in some sense that the whole this whole guy doesn't depend on the lattice in some, yeah, but yeah, this is very, you can see it very concretely at this level here. Okay. Right. Yes. So there's a, yeah, so you can extract from this that if V is a complex vector bundle, then, well, I'll just do the simplest case. So if you take the first Chern class of V and you take it mod 2, this only depends on the associated spherical fibration. Because the first Chern class mod 2 is just the second Stiefel-Whitney class of the underlying real vector bundle, and then you apply Thom's observation. So you can do the same story in this oh no, okay, wait. I should never have gone to 3 boards. Okay. I don't know if this is the correct way to do it, but. Okay. So, right. Right, so again, so if you have an invertible Lie SL sheaf on S étal, then you get actually a class in, no, L equals 2 now. So I'll take S2, we want to pick up the 2 torsion information. Then we get a class in H2 of S with coefficients in F2. And for the sphere on a vector bundle, this is, well, it's the mod 2 reduction of the first étal Chern class, but this is just the gerb of square roots of the top exterior power of the vector bundle. So if V is a line bundle, it is the gerb of square roots of the line bundle. And for SL, well, it's non-trivial. So, so in the universal case, what we get from such a cohomology class is a central extension of GL and Q nu, and this is of metaplectic type. So it's a non-trivial central extension. If n is even and you restrict to the symplectic group, it exactly produces this metaplectic double cover of the symplectic group over your local field. Okay, now I want to make a remark here. So note that this depends on more than just the dimension of the vector bundle. So in our first 2 invariants, or the rank of the vector bundle, well, the dimension was just twice the rank, but also the orientation twist, this thing was just a Tate twist determined by the rank. And it's a kind of a familiar from étal cohomology that those are these orientation sheaves that you have, they only ever depend on the dimension of the vector bundle. But once you look with sphere spectrum coefficients as opposed to working over the integers, then actually it's a lot more, it picks up a lot more refined information about the vector bundle. In particular, if it's a line bundle, it can tell whether that line bundle has a square root or not. Okay.
Sorry.
Yeah.
You never explained in for Hodge theory how you deal with second grading.
Yeah, it's coming. Yeah. So that's another. So I think I'll turn to that now, in fact. Yeah, I should say there's many more invariants you can extract. Yeah. But let me maybe get to stating the conjecture. So okay. Yes.
In the last line, what do you mean with universal case?
Oh, yeah, so this sphere that you can extract, it's not just for an étale site that you can do it. You can do it in any topos, any site. And the universal case for a Lis Q nu sheaf is like the topos BGLN Q nu. And if you do it in that case, then such a cohomology class gives you a central extension. Okay, right. So, now let's, okay, so now let me make a strange definition. So let's, again, S a Q scheme, and M a motive in S. So, so we define, I'm going to define something I'll call the Lie algebra, or the Lie, well, no, not Lie, it's just a vector bundle, but, well, it's actually a virtual vector bundle, so it's going to be a class in K-theory. I'll call it the Lie algebra of the motive, and you're going to get it from the Hodge realization. You take the pth piece, you direct sum over all p and z, but then you repeat the pth piece minus p times. Okay? So it's a virtual vector bundle because sometimes you're taking negatives and so on. So this is a very funny expression, so I should maybe say a bit about where it comes from. So what is the meaning? Well, one thing you can say is that, in fact, this expression has appeared before. So, so in the context of variations of Hodge structures, so the top exterior power of this thing, the determinant of this thing, or maybe I think it's actually its dual, is the canonical bundle of Griffiths. Yeah. So it's the line bundle you build when you have a variation of Hodge structures, which he uses as his ample line bundle when he's proving that images of period maps are actually algebraic. So it's this very vector bundle here, the line bundle, the determinant of this thing up to some sign, and also for S equals spec F, a number field F, this same determinant of Lie algebra with the dual is the ingredient in Kato's heights of motives. So he defines, so Kato, this is just a one-dimensional F vector space, but Kato puts a norm on it at every place and then extracts a real number from that, a positive real number, which he calls the height of the motive. But it's the same guy that's coming into it here. Okay, so that's sort of where this bundle, or rather its top exterior power, has appeared. But what is the meaning, the true meaning of it? So, all right, so the true meaning. So it sort of comes from Hodge theory. So if you look at in the modification of vector bundles, on twistor P1 in the case of usual Hodge theory, or Farg-Fontaine curve in the case of p-adic Hodge theory, perspective on Hodge theory. This Lie algebra of M is the amount of modification. So, for example, in the twistor P1 picture, a reformulation of Hodge theory given by Simpson explains that to a pure Hodge structure, you get two different vector bundles on P1, and they are isomorphic away from the point infinity, which has residue field C. And so then at the completion at C, you get two different lattices in the same Laurent series field. And you can measure the relative position of those two lattices by a virtual vector bundle over the complex numbers. And it is that virtual vector bundle. And it's the exact same story in p-adic Hodge theory up to some Tate twists, which it turns out won't be relevant for us. But then this object, which measures the amount of modification, actually exists completely globally, even when you don't have any Hodge theory. So it's good to consider. Okay. So, and let me give an example. So if you have an abelian scheme, then the Lie algebra of the, I guess the dual to the usual H1 is just the Lie algebra of the abelian scheme. So in that case, an honest vector bundle. Okay. So now let me state the conjecture. So again, I'll, for the moment, stick to the case of Q schemes. And then we take a motive. So it's going to be an expression for, and then we take L an arbitrary prime. So it's going to be an expression for the sphere attached to the Lie algebra of this motive. So that's something that came from the Hodge realization, but it's going to be an infinite tensor product over all primes nu of the sphere attached to the L-adic realizations. So this is, or nu-adic realization. The infinite tensor product has meaning because if you have a motive with Q coefficients, it always comes from a motive with Z1 over N coefficients for some N. And then, as I said, these spheres are canonically trivial if L is different from nu and you choose a lattice. So kind of, yeah. But there's another way of saying this. You could also say this is a, yeah, you can also define this in the same way as sphere attached to, you could collect all of these nu-adic realizations into like a, an adelic realization. And then this thing would be, give a more precise meaning to this infinite tensor product here. Okay. So now I want to say what the evidence is for this conjecture and what the consequences are. And maybe somehow it's the same thing. So I should have done this one. Oh, shoot. Oh, I forgot the most important hypothesis. Oh, no. And it's way up there. Okay. Oops. Ah. Oh, no.
You can push the others.
What?
You have to push the others.
A motive of weight -1. Okay. So evidence. So first of all, it's true if M is this. So one way to get a motive of rank 1 is to take one of these R1 F floor star Q for F A to S in a abelian scheme. So for the motives attached to abelian schemes, this is a theorem that I showed. Yes, the dual H lower 1, yeah. Yeah, so H upper 1 is weight 1, H lower 1 is weight minus 1. That statement's true for weight minus 1, but not true for weight 1. The second thing is that it's true if there exists a map from S to spec Q bar. So if your scheme lives over an algebraically closed field, then the conjecture is true. And here the proof is by Hodge theory, by real Hodge theory, or complex Hodge theory. So you can, by standard arguments, assume it's actually over the complex numbers, and then you can apply Hodge theory, in particular the Betty cohomology. And because of this, the statement itself is some kind of a claim that there's some hidden Galois equivariance in a purely transcendental construction. So you can make an identification like that using Hodge theory over the complex numbers, using the existence of Betty cohomology, but both sides make sense over Q, and then the claim is somehow that this isomorphism you produce using Hodge theory descends to Q, which is quite mysterious. And it's related to Taniyama-Shimura type reciprocity laws, as maybe I will explain.
Sorry, I'm a little confused. So MS, is it a conjectural category MS, or you're really taking some concrete MS? So the category of motives here.
No, you see, the way you should read this, one way to read this, for example, is that if you have a smooth proper S scheme, and then you take some HI of that thing, and let's say you take I to be odd, and then you Tate twist down to get into weight minus 1, then you know how to write down all these realization functors, and then the statement makes precise sense.
If you have an idempotent, like an algebraic cycle.
Yes, then you can go ahead and try to do that as well, yeah.
But you don't know it, like over Q bar.
Well, no, I mean, no, sorry. We're really, the coefficients in our motives are really Q here, not Q bar. Or is that?
But, so what is true over Q bar?
When S is over Q bar, this, yeah, what's true is actually a statement about variations of Hodge structures. So any time you can write down a variation of Hodge structures over the complex numbers, then you get a theorem like this.
So I want you to clarify. So if you have over Q bar, so let's say you have something smooth of finite type, is S is not necessarily smooth, or okay, I'm not sure, because in the usual theory of variation of Hodge structures, S to be.
Yeah, that's true. But you know, but the claim everything has a tall descent, so you can kind of use resolution of singularities.
Okay, so the question is, the real question is, so if S, let us say, even smooth over Q bar, and you go to C. But there are several embeddings to C. So each time you have an embedding to C, you say you have some transcendental recipe, and those are compatible, or you just choose one of them?
You just choose one of them, yeah, exactly. And then, yeah, so even here there's kind of a, even there's a claim. So I said exists, but to make it canonical over Q bar also it's not clear. Yeah, that's a good point.
But do you expect from looking at cases where one is more theory, like abelian schemes, is it the case true for abelian schemes that what you get from different embedding to C are compatible?
Yes.
So therefore you say that it should be in general, and is it enough to prove this compatibility to descend from Q bar to Q, or you need more information?
Yeah, I mean, in principle, to me, you need more, but since I don't know how to do either, I don't really know how to answer the question. Yeah, so, well, third, maybe I won't write it down, but there's this analogy between motives and these T motives in the function field context defined by Anderson, and I will say you can formulate an analog of this conjecture in that context, the function field context, and then you can actually prove it, and it's not even difficult to prove. So I'll just say the T motive analog is true. So for me, that's pretty compelling theoretical evidence. So now let me try to explain what this is saying concretely, or what you can concretely extract out of this conjecture. So well, the first thing we can look at is just dimensions. And so take dimensions, and we deduce for m of weight minus 1 that twice the dimension of the Lie algebra of m is the same, or I was using rank, I'm sorry, is the same thing as the dimension of the nu-adic realization, so for all nu. So to get this, you choose L equal to nu, and the only sphere that's contributing on the right-hand side is the nu-adic one, and it gives this, and that gives that. So this kind of implies, you could say, note that this doesn't depend on nu, that a priori does depend on nu. So this, I guess you could say, gives independence of Betty numbers. So these things do not depend on u because they're equal to that thing. But also it gives you that the Betty numbers are even. In the case of weight minus 1, or more generally in the case of odd weight, because you can always Tate twist down to get to there. And these are known facts. The usual way of seeing that the Betty numbers are even for odd weight is to use some kind of polarization or there's some symplectic form, but this is kind of a different explanation. You could say you're actually finding the thing, the canonical half-dimensional thing there. And okay, this independence of Betty numbers in characteristic 0 is not so impressive, but I'll say there exists a form of this conjecture also over Fp, and it likewise implies this independence of Betty numbers and the evenness of the Betty numbers in odd weight. And there those are more serious results proved by Deline. Very much not obvious. And of course, I haven't proved it either, because this is just a conjecture. I'm just trying to explain what the conjecture predicts, yeah? Right. Okay, likewise, if you take this second linear invariant, this determinant thing, then you discover that the top exterior power of this thing has to just be some Tate twist for all nu. Has to be the appropriate Tate twist. So the only sort of one-dimensional motives of odd weight that you should ever see are just Tate. Oh boy, wait. You know what? I'm just going to stick to 2 boards from now on. Okay, so what about these more refined, these higher invariants? So I want to extract something from these nu2 gerbs. So let's take S to be the, a moduli stack of elliptic curves over Q. Then the conjecture implies, and in this case this is an honest argument because the conjecture is true in the case of abelian varieties, and in particular for elliptic curves. So what you extract is that, well, yeah, first of all, let's say 2-adic sphere attached to the Lie algebra of the universal elliptic curve, which is the so-called Hodge bundle, is the same thing as the 2-adic sphere attached to the finite adelic Tate module of the universal elliptic curve. And now if you pass to the moduli of elliptic curves with full level structure, then what happens over here is, well, this Tate module by definition gets trivialized. So then on that level, this is just the trivial sphere. And if you look over on the other side of the equation here, and recall this Stiefel-Whitney class living in degree 2, which controls square roots of line bundles when you plug in the sphere of a line bundle, what you deduce is that, deduce is that on the moduli stack of elliptic curves with full level structure, there exists, in fact, canonical square root of omega. And moreover, if you believe a functorial form of the conjecture, so kind of functorial for automorphisms, which is again true for abelian varieties, moreover, this omega 1/2 is equivariant for this, so GL2 of the finite adels, this double cover of GL2 of the finite adels acting on moduli stack of elliptic curves with full level structure. So on the moduli stack of full elliptic curves with full level structure, you have GL2AF acting by changing the level structure. In particular, you have this central extension acting, and omega is equivariant for the non-central extension one, which is why you have Heck operators on modular forms from an algebraic perspective. And what this is saying is that, well, this explains in some sense why there's a theory, algebraic theory, of weight 1/2 modular forms with Hecke action. So there's actually this was the starting point for me for this whole thing, because I saw a talk of Deline's, which is online on YouTube at the Mostow Fest, where he explained this formulation for the algebraic theory of weight 1/2 modular forms, and then I realized it should be connected to these spheres. So note that this 1/2, essentially it's coming from the fact that the first stable homotopy group of spheres is a Z mod 2. That's what's giving you this second Stiefel-Whitney class and all these other things. And so it's the same 2 that's appearing there, and so kind of maybe the reason why you don't have modular forms of fractional weight having an algebraic meaning is connected to the fact that this is precisely Z mod 2 and not Z mod 6 or something like this. Right?
Do you
have a conjecture for even weights?
Yes. Well, not right. Okay. Let me check the time before I answer your question.
You have 20 minutes.
Okay. I'll get to it in a sec. So one more concrete consequence. Yeah, no, maybe this takes a bit too long to explain. Well, you can soup this up a bit because, well, you know what? Maybe I think I've maybe. Well, let me just say you can. Yeah. I'll see. So if you look, for example, at if you take f to be imaginary quadratic, and you look at the moduli stack of elliptic curves with complex multiplication by f in full level structure over Q, then this is actually just, I guess, spec of the maximal abelian extension. And you can really prove this just from that conjecture, which is very funny because this is just a bunch of torsion stuff, but here you have something quite substantial. So there are various tricks for upgrading this to give more refined information in the presence of complex multiplication. So what you can do is if you have a motive with endomorphism ring F, then you can apply this conjecture not just to that motive, but to that motive tensored with any finite dimensional F vector space. And so it upgrades to a statement involving the K-theory of F, algebraic K-theory of F, and that contains a lot of information, and if you play around a bit, you can actually deduce some cases of Taniyama-Shimura reciprocity laws just from this bare conjecture, which is sort of surprising.
Sorry, this is equivalent as what?
It's isomorphism of schemes. Yeah. Yeah. Right. Okay, so maybe I think there were a couple more things I was potentially planning to talk about. One of them was what happens over a finite field, or in characteristic P. I think I'll skip that, although it's quite interesting. And instead I want to talk about maybe why this weight minus 1 hypothesis is there and how one might get rid of it. So yeah.
Specific questions on the right, you have stack of a cube, so
Yeah.
point.
Yeah.
On the left, you have something that is complicated.
Yeah.
How do you do this measure?
Well,
How can I understand this?
Oh, yeah. Well, you can understand this by thinking about what the C points of this is, and then you see that there aren't that many, in fact. It's just, so if it wasn't a full level structure, but some finite level structure, it would just be a finite set of points. It's basically only finitely many isomorphism classes. And full level structure, it's profinite. And then it just turns out that the descent data for writing it over Q instead, or, well, it actually lives over F, is the same as, so it's, yeah, if you look up, if you read, for example, Silverman's book, Advanced Topics in Elliptic Curves or something, then you find a nice explanation of this sort of thing. Maybe not precisely in this language, but it's a, no, well, yeah, I don't know.
So these are elliptic curves have complex multiplication.
Yes. Yeah, so it's like you have the moduli of elliptic curves, which is big, one-dimensional, and then you have the CM. CM is just a finite set of points, really. And then with full lever structure, you take some inverse limit, it's a profinite set, and it turns out to be this one when you think about the descent data. It's a beautiful story, so yeah, but I really don't have time to get too much into it, but it's a beautiful kind of classical story in number theory. Okay, why weight minus 1? So, well, you can look at the basic fact. So in terms of twistor P1, so weights correspond to slopes. Is that what they're called? Yeah. Slopes of vector bundles on P1. And the basic fact is that if V is semi-stable of slope minus 1, then the total cohomology of V is equal to 0. So
what do you mean exactly by P1 R, this twist of P1? Is it just because in Simpson, I mean, you could it's the usual P1 over C with some extra structure, or what is it? What is it exactly?
yeah, so for this statement, I'm just thinking of it as an R scheme. So it's the non-trivial form of P1 over the real numbers. It's a very Brouwer variety of the quaternions. But yeah, you have to be a bit more careful when you're doing the story in families, but I'm just trying to give the idea here. Right. So what is the relevance of this? Well, actually, so there's something funny about this statement, which is, usually you have, this is part of a family of statements which includes, for example, Hilbert reciprocity. Some statement about product over all prime numbers of some local data is trivial. But note that we're missing, in the nu is running only over finite places, so we're missing the infinite places in the nu. Now, you might be tempted to move that sphere of the Lie algebra over to the other side and call that the infinite contribution. I was tempted to do this, and it blocked me for several years. That's absolutely not what's going on. So what's going on is that that Lie algebra thing is some discrepancy that shows up that's not attached to the infinite place. And the contribution from the infinite place is missing. And in fact, it disappears. The contribution at the infinite place should, so this is this suggestion of Scholze in his ICM address. So something sort of vague that the twistor P1 realization should exist over an arbitrary S. So it's a story that comes from Hodge theory, but he says in some sense it should make sense over an arbitrary scheme. And so we're missing a realization functor on the right. There should be a contribution from the infinite place. And it just happens to be that the contribution vanishes in the case of weight -1, essentially due to this fact. And this is exactly what's happening in the proof of that conjecture in the context of Hodge theory. If you phrase it in Hodge theory in terms of modifications of vector bundles, it is this fact which means that some extra contribution is vanishing when it comes to the conjecture. So yeah, I have some sort of I can make precise some sort of weak form of this, to address your question. I can make precise some sort of weak form of this conjecture. I think I won't do it in this talk, which would then allow you to make a conjecture for all weights there. But it's a conjecture about it. Well, it's two, yeah, this usual story with motives. There's two conjectures. But you can actually test it because, in principle, because you could take the difference, like everything there is well defined. If you start with a motive you know how to write down, then you could take the difference between those two spheres and ask whether that sphere is associated to, say, a real vector bundle over the étale site, or at least some homotopy shadow of a real vector bundle over the étale site. And the prediction is that yes, it is. So the discrepancy of this being satisfied outside the weight -1 case should be controlled by something like a real vector bundle. But I think I won't take the time to make that precise. And in fact, I think I'll just stop here. Thank you for your attention and your patience.
Okay, so we will take a few questions from Tokyo, from the morning side, and maybe we start with Offer before coming back to IHES. So Offer, do you have questions?
So if you can do it in a short time, can you say what modification is needed for S not over Q or in positive characteristics? So of course there is a problem of the mixed characteristic case.
Yes.
You don't know which homology theory you use. You need some mixed thing with, so you need maybe to invoke the prismatic thing, quite, I mean, or maybe you just restrict to S of Q characteristic. What do you do?
Yeah, good idea, because indeed in mixed characteristic it is complicated, but in FP it's not too complicated to say. So there you don't have the Hodge realization because we're working with motives with Q coefficients, so you simply don't have the Hodge realization. So you just leave out the term, well, you make the term on the left-hand side trivial. And then, but as a compensation, for nu equals to P, you have this crystalline theory, which has a lot of extra stuff. It's it's more meaty than the L-adic realizations. You can define exactly an L-adic sphere on the étale site of your FP scheme for any L, including L equals P equals nu. And then the conjecture is that if you do that there, then the conjecture, if you just make the trivial sphere on the left-hand side, that's the conjecture that holds. And what's secretly going on is that in the passage from characteristic 0 to characteristic P, the spheres for the p-adic realization and the sphere for the Lie algebra, which exists in characteristic 0, kind of get combined or to form the sphere attached to the isocrystal realization. Yeah, and I can make precise like the manner in which that's happening and so on. It has to do with Farg's kind of perspective of the modifications of vector bundles on the Farg-Fontaine curve. You can also see it quite explicitly at the level of these low degree concrete consequences. But yeah, that's the basic story, is you just leave out the thing that doesn't exist and you get I claim a true statement, although I can't prove it.
Okay, is it both for, I understand this is both for L equal to P and L equal to P?
Yeah.
Okay, so that's and in both cases you use only the okay. So.
Yeah, the weird thing is that even in characteristic P, like you know, I had these least SL things. You really do just look at least SP things on the étale site. So it's there's no isocrystal anything on the L part of the story, only on the nu part of the story. On the L part of the story, it is still just the étale site, and usual least sheaves, well, just with sphere spectra instead. That's kind of the funny aspect.
Okay, so we move now to Tokyo. So Shane, could you do you have questions?
Let me make one stupid question. So, yeah, so you take product of prime numbers. So that reminds me L function. So do you expect some relation with Tamawa number conjecture by Broca's cutoff?
No, I think it's a different story. And the reason is that that's something very specific to motives over a number field, whereas this is motives over any base. So I don't see the precise connection, yeah.
Thank you.
Okay, and then the morning side.
Any questions? So there's no question for me.
Thank you. So, and then at IHES, do we have any question?
So may I ask a silly question? I mean, it's very. I mean, in the previous picture, I mean, you somehow start with, I mean, smooth proper schemes over this, but I mean, if I understand correctly, I mean, tau and S, they have some non-commutative, I mean, story of this. I mean, for DG categories, do you have similar picture in that? I mean,
no, I don't. No, I mean, well, I don't know what the story with weights is in the non-commutative context. Yeah, no, yeah.
Other questions? Yeah.
Yes. So you mentioned T motifs. What would be the replacement for the sphere spectrum in that?
No. Well, no, it's still the sphere spectrum.
But how do you L complete for L monic irreducible?
No. Sorry. Yeah. No. It's still, you have to, again, you choose a prime. So there you have 3 primes as well. Okay. The first prime is always P. The second prime nu, that's now a place of your function field. The third prime L is still just a prime L.
Different. Okay.
Yeah.
Okay.
Yeah. And actually, in that case, L does have to be different from P. But anyway. Yeah.
Christophe?
Yeah, I don't have a precise question, but there is this theorem of Deligne that any Hodge cycle is absolute Hodge. Does it play
on an abelian variety? Yeah.
Abelian variety, does it play any role in your story?
No, not that I know. Yeah.
Okay, so
one more.
Yes, please.
So you mentioned the Stiefel-Whitney classes, and so F2 appear.
Yes.
So our standard operations, the standard squares appearing.
Yes. Oh yes, right. That was Tom's definition. Basically, is you take if you have a spherical fibration, then it's always oriented with F2 coefficients, and then you have this so-called Tom isomorphism, but the Steenrod action gets twisted, and if you look at how so you transfer via the Tom isomorphism up to the sphere bundle, apply Steenrod operations, then transfer back. Those are the Stiefel-Whitney classes. That was Tom's theorem.
And they do appear in your story then?
Well, I mean, there are also other ways of defining these, only insofar as they contribute to one possible definition for these Stiefel-Whitney classes. There are other possible definitions, some of which I prefer for my own personal reasons, but yeah, so. Yeah.
Sorry, can I ask a question?
Yeah, please.
Sorry, so for each realization, you build like a Fourier spectrum like this.
Yeah.
Do you expect to see something like in motifs, like in SH? Independently of the realization, having a formula like this written in SH?
I don't think so. Yeah, it's a bit of a puzzle for me. So certainly for the sphere attached to a vector bundle, it exists as a motive in SH or whatever. But for the other ones, a priori, no. But I'm not, yeah, I don't know. Yeah, the other, yeah. I mean, at the very least, for the isocrystal story, the usual SH won't be good because of the A1 invariance being broken, but yeah, but maybe there are replacements. I don't know.
Because you don't see the A1 invariance in this story.
No, well, in characteristic 0, wait, what? Well, no, I mean, if you work with the in characteristic P, there's also a story with p-adic least sheaves, and that theory, yeah, so there you wouldn't have any, I mean, that doesn't come from a realization functor on SH, yeah.
Okay.
One question.
Yes, please.
Did you say at some point that this story includes the law in class field theory?
No.
You said the fact that the sum of the invariance is equal to 0 for something global.
Yeah.
I thought you said that. No?
Well, it's reminiscent. So, but in fact, actually, in some sense, well, right. So, in fact, you can.
So the question, you would extract from your conjecture. You would extract.
Not from this one. So I was saying you can get you can get this. Explicit class field theory for imaginary quadratic fields, but no. But if you look at you can also make a conjecture for motives of weight 0, and I mean a very simple one. So like if you have a tall local system of Q modules, a very simple example of a motive of weight 0, then you can make a precise form of this conjecture which includes the infinite prime, and I proved it. And that case actually is strong enough to give Artin reciprocity. So actually, I actually did write a paper about.
So you mean the conjecture implied Artin reciprocity?
Well, a form of the, yeah, if you make the strongest form of the conjecture, then it implies Artin reciprocity. I mean, you have to, there's a big thing you need to know to make that deduction, which is that a number field has virtual cohomological dimension less than or equal to 2, so it's non-trivial, but that's basically all. Yeah.
Okay, other questions? Okay, if not, let's thank Dustin again.